Up to this point, everything we've been talking about in chronoamperometry has been for a single species being present in our electrolyte. However, that's not always the case. Sometimes you have multiple species presence that you want to analyze in your electrolyte. If that's the case, we're going to have to probe along a broader potential window to find where we can apply the Cottrell equation, if possible. Just like we did when finding the diffusion limited region, we're going to look across our cyclic voltammogram to find the different peaks where we could possibly be getting diffusion limited. And here a simple illustration is we have steps 1, 2, 3, and 4 across 2 peaks. This is for gadolinium reduction followed by lanthanum reduction. What I'm going to do is I'm going to try and tune step 2 and maybe a couple steps in there so that I get the gadolinium diffusion limited current before lanthanum starts to deposit. And then I'm going to record maybe at step 4 the diffusion limited current of gadolinium and lanthanum combined. But if I previously know the diffusion limited current for gadolinium from step 2, I can then subtract that out to get the properties or concentration of lanthanum. What does that look like? Well, here's the calculated diffusion coefficient at a number of steps going across those 2 peaks. And you can see that we get a clear plateau further out for the lanthanum and gadolinium diffusion coefficients. But for gadolinium, we almost get a nice plateau, but it doesn't quite completely flatten out. This means that we maybe have 2 signals that might be a little too close for using chronoamperometry. But for illustrative purposes, this gives you an idea of how you could go about applying chronoamperometry to multiple analytes in solution. Ideally, you'd end up with a bit more diffusion coefficients calculated here that are about the same before you start getting variation again. When applying chronoamperometry for multiple analytes, the problem is that you have little potential discrimination because your currents are overlapping in a diffusion limited regime. So it's hard to tell from chronoamperometry whether one reaction is occurring or 2. As I showed, the workaround is you use many applied potentials. However, you need to have 2 or more potential independent regions to do this for multiple analytes. And as you saw on the previous slide, I didn't quite have 2 potential independent regions. The limitation is that you need a large difference in the equilibrium potentials to use this technique. Typically around 100 millivolts or more spacing between the 2 reactions. If you're going to do this, it's often more efficient to use normal pulse voltammetry, which will be covered in some later lessons. So chronoamperometry isn't the best for doing multiple analytes, but there is a way to do it, as I've illustrated. Last, we've been talking about chronoamperometry this whole time. Chronocoulometry is a really useful way to use the exact same data. The only difference is you're now going to integrate your current over time. And so if I take the Cottrell equation and integrate it, I get this expression for my diffusion limited charge. Now, what's really nice about this is rather than having my signal decay with time, it grows with time. So this increases my signal to noise ratio. Notice how the t to the 1/2 came into the numerator when we integrated. It also helps us identify contributions from double layer charging and absorbed species because those occur very, very quickly. Double layer charging, as we've discussed in previous videos, applies on very short timescales. And if I have species absorbed on my electrode, they're going to react immediately when I change that potential. So you're going to end up with a total charge that consists of my diffusion limited charge, my double layer charge, and then the charge from reducing my absorbed species. This is my concentration on the surface or my surface excess of my oxidized species. Now, these together are really fast that they just simply show up in chronocoulometry as my y-intercept. So here I have about negative 50 microcoulombs of charge, and I can attribute that to double layer charging and or absorbed species. And then further out, I just only have my diffusion happening. So I can get from the slope of this line further out here, my diffusion coefficient, concentration, whichever I may be searching for. And that wraps up everything we've planned to cover for chronoamperometry. If you want to dig in more, you can go to the website lesson and see all the resources posted there.